All right, I'm starting here at Article 21011. Let's read it real quick, and then we'll go over to the code section it sends us to. It says, and we did this one yesterday, but let's just go over it again. Branch circuits for lighting and for appliances, including motor-operated appliances, shall be provided to supply the loads as calculated in accordance with 22010. So if we jump over to 22010, and here I have 22010, you don't have to write any of this down right now. These are all articles, so we can just go highlight them as needed. So if you look at 22010, this is what you get. Now, for those of you who went over here yesterday, hopefully, and this is why I sent you there, it prompted you to go into all of those. If you didn't and you just looked at it, okay, no problem. But the reason why all of those are included there is because all of those are the knowns about the buildings that or the things that are going to go into the house, as I was describing here, the water heaters, the ranges, and etc. So it says branch circuit loads shall be calculated in accordance with and a bunch of articles. 22014 for other loads, all occupancies, kind of vague. For additional or additions to existing installations. For dwelling units, for lighting loads, for remember how I said that they describe it as non-dwelling unit occupancies? And for hotels and motels, as I said, they kind of fall under a house. So the one we're going to look at today is that one, 22041, which I have right here below. And this is how, whenever you are going to start a load calculation for a house, this is the first calculation you make. All right, this is the first calculation you make, which says, if we read the article here, in one family, two family, and multifamily dwelling units, we're only going to do one family dwelling units, just as our examples. But bless you, bless you.
Thank you.
In one family, two family, and multifamily dwelling units, here comes that VA again, the minimum unit load shall not be less than 3, we're doing this one, we're ignoring meters per square foot, we don't calculate it in that, 3 VA per square foot. All right, I'll write that there, 3 VA per square foot, which is represented like that, foot squared. All right, so right now, the only real thing that you need to do, I mean, you can go to the code section 22041 and highlight it, but we're not doing that article today. So while you have highlighted it and good to go, we'll get back to it in a couple of weeks. This is the only real number you need to pull out of all of this, 3 VA per square foot for, and let's now take a page here and start to write this as a note. All right, it's 3 VA per square foot for, and I'm going to write it like this, general lighting loads, called general lighting loads. In parentheses, I'm going to remind you that these are receptacles. That's what that means. You can write it all out if you want. I'm just saving space. And lights. All right, these are, and if you want to give this receptacle an even more description, you would say general purpose receptacles, if you wanted. All right, go back one. All right, so actually, let me bring this over. Where do I want to bring this over? Let's bring that over to there. Okay. So when we're looking at a panel, right, when we're going to start to set up a panel for a house, right, we have a house, we got to whole house that we're going to wire up, we got to figure out panel size. And by panel size, I don't mean how big does this thing have to be. Although, yes, we also want to know how many spaces are involved in the panel. There is a main breaker here that we are going to size. This is going to get sized by Article 220. So we're not doing that one yet. Determine that one, you have to figure out everybody. So as you start to build your panel, right, and you're starting to determine everything that's going to go into the house, as I said, yes, you have a whole list of things that are going to go into the house, but you also have the general purpose receptacles that are in the walls, right, in the bedrooms, in the living rooms, in the hallways, that may or may not have something plugged into them, which we don't know when they will be used, what will be plugged into them. Right? All the outlets, think about the outlets in your house that you have. Some of them aren't doing anything. Some of them have never had something plugged into them. I know there are outlets here I have not plugged into anything yet. Some of them do. Some of them have a lamp. Some of them have a TV. Some of them have a laptop connected to it. My computer's connected to an outlet. Refrigerator, etc. Outlets, some of them are in use. Some of them are not in use. So when you're trying to figure that out, how do you place a number there? How do you say, this is how much amperage we are going to give these outlets to deal with? Now, you could always go buy the biggest panel that they make, which is 42 spaces. Put a bunch of 20 amp breakers in here, just a bunch of them, right? Put 30 of them in there out of the 42 spaces. And then just wire up a bunch of outlets from all of these breakers. In other words, you can go completely excessive, and if you know more or less what you're doing there, you can just put a bunch of breakers and set all this up. But we don't want to do it that way. We want to make calculated determinations as to how many breakers we're going to need. So for things like, going back, for things like the water heater, I know the size of the water heater, so I can calculate and determine that breaker. For things like the range, I'll determine that breaker based off of the one we're getting. Same thing if we have a dryer. Same thing if we have a, what else do we want to put in here? Right? Water heater, etc. But the ones that are general purpose, you can't use anything in particular. You can't ask the person, hey, what are you going to plug into this outlet? Is it going to be your lamp or your TV? And can I see the TV? What kind of light bulbs are you using? This is just something that you have to determine based off of a calculation. So here's where the code book comes in and sets 3 watts. Right? Remember, VA and watts are the same thing. We just say VA because A, we're electricians, and B, we're talking about a calculated number here. So the code book says, to determine those general purpose lights and receptacles in the house that, again, you don't know what they're going to be used for, we're going to set 3 watts as the minimum wattage per square foot of the house. All right, so this is the first calculation that we're going to make. So you have a house, any house, and this goes for small, large houses, and this is where, going back to that spectrum that I put, little house versus massive mansion. Well, it's the square footage of this one that starts to be the first calculating factor between the small house. Just square footage alone. So here we get to set a determining calculation for the area of the entire house. So I'm just putting a square here. All right, you know, houses have weird setups. There may be here, there might be a second floor on the house. Who knows? Whatever the square footage style of the house is, doesn't matter. I'm just putting a square for super ease. And also to teach, if anybody's not ever calculated a square footage before, just kind of show you how that's done. You just multiply one side and only one side by the other side, and pick any side you want. If you had a second floor, then you just do this twice. If you had a basement, then you'd add the basement. If you had a couple of things, you add. When we get into Article 220, we're going to actually get a better breakdown of what actually is square footage that we're going to calculate versus square footage that we're not going to calculate it. Like the attic, we don't include the attic. We don't include the porch around the house. We may or may not include the garage. It all depends. We'll get that better breakdown in the article. So for now, let's just use any numbers here. Let's say we have 50 feet by 50 feet. So you just multiply those two. So 2,500 square foot house. Big house. All right, we can say 2 stories. So not too big. 3 2-bedroom, 3-bedroom, 2-bath, 2 stories. Easily you'll get this square footage. So to determine how many breakers you are going to need for all of your general purpose outlets that are going to be around the house, this is the first calculation. You'll multiply 2,500 times 3 VA. And this will equal a total VA at the end of that. So 2,500. If anybody's got that number, let me know.
7,500.
7,500. Very good. 7,500 VA. So that's what the code book is saying. We can give minimum. We can always go bigger. We always just deal with minimums as we do our calculations. The wattage for that area is going to be set at 7,500 watts for that area. So that means all of your general purpose outlets around this house, when people start to plug things into them, they'll be covered up to 7,500 VA. All right, it takes a lot to get there if you're just plugging in lights and TVs and stuff like that, so that's plenty. But then how do we get from there to breakers? All right, how do we get from there to breakers? So the next step here is Ohm's law, because this is what we've done. The first, we've described wattage. So from here we do Ohm's law, 7,500 VA, and now we're going to divide it by a voltage. Now, this is why 210.6 was before this one, because 210.6 gave us the voltage that this has to be. All right, just to remind you of that, I'll go back up to that article. 210.6 yesterday when we looked at it said branch circuit voltage limitations for dwelling units shall not exceed 120 volts. All right, in dwelling units and guest rooms, like I said, similar occupancies, the voltage shall not exceed 120 volts for those general purpose receptacles, luminaires and cords plugged in devices like, again, lamps, TVs, computers, not exceeding this wattage, which they will not, right? 12 amps is a lot for, there's no computer that you have that draws 12 amps. Unless you're mining a little bit of Bitcoin at your house. and very little, 12 amps is very small. So we have the voltage. It will always be 100% of the time when we do the calculation to determine how many branch circuits, go back again to where we were at, how many branch circuits we need for a dwelling unit. We will always divide, sorry to have rushed through that, how to determine the branch circuits for a dwelling unit. We will always divide by 120. All right, so we make this division. We come up with I, and everybody should be looking at 62.5. 62.5 what? Amps. All right. Are we following so far? So you have this area, this space, this house. It's going to be a house. Just an idea right now. It's not even a building. It's just dirt. We haven't even laid the foundation yet. We have this idea for a space. You got to put a bunch of outlets here. All right, you got to put a bunch of outlets. And soon we'll find out spacing. How far do these outlets got to be? Got to do a bunch of stuff with those outlets. So the first thing you have to do is this. Determine the square footage, 3 VA per square foot. Come up with a total wattage. Divide by the 120. And now you've come up with a total amperage. how do we get from here to breakers? Well, let's go back over to the code section 21011 and look at what A and B are saying. All right, what A and B are saying. So if you look at A is saying the minimum number of branch circuits shall be determined from the total calculated load and the size or rating of the circuits used. So basically what this is telling us is that we're going to calculate how many branch circuits we need based off of the loads that we're going to connect to these things, right? The loads that we're going to connect to the panel, and the size or rating of those loads. If you look at B is saying where the load is calculated on the basis of VA per square foot. Again, we ignore square meters. The wiring system up to and including the branch circuit panel boards shall be provided to serve not less than what you've calculated. So you got to find a panel board that can handle the amount of amperage that you've calculated in the whole total. And this is the part that will involve the amperage that we calculated. This load shall be evenly proportioned among multi-wire branch circuits with the panel boards. Branch circuits, breakers over current devices, and circuits shall be required to be installed to serve only the connected loads. All right, so what does all that mean? That means this. One is you'll use 3VA to come up with a total wattage. And then when you come up with this amperage, you're going to divide this over proportionally. You're going to divide it proportionally over the breakers. So with that 62.5 amps, the next step is to divide this over a breaker size that we are going to have for our general purpose outlets. Now, unlike this 120, this one is a one or the other. You can use one or the other. You can use 15 amp breakers for these general purpose outlets, or you can use 20 amp breakers for these general purpose outlets. Now, it gets even a little bit more complicated than that because there are areas in the house that have to be 20 amps, and there are areas in the house that can be 15 amps. But to not complicate it too much, the questions that I'm going to give you are just going to give you the breakers that I want to determine how many we need. So for example, for this 62.5 amps, I will say, or technically going back one, for that square footage, I'll ask, how many breakers do I need for 2,500 square feet? And when I say breakers, I'll say a size breaker. So how many 15 amp breakers, or 20, but 15 amp breakers in this example, do I need for 2,500 square feet? So good, you want 15 amp breakers for 2,500 square feet. So I start, multiply by that, come up with this number, divide that number by 120, amperage, and now divide that by 15. So 62.5 or 63, it wouldn't have mattered if you did that. You could round up in these cases. Divided by 15 comes to 4.16. Now here's a very important note. And I'm going to erase this because we really don't need it, because I'm not going to give you a shape and then ask you to determine the square footage. I'm just going to give you the square foot in the question. I just wanted to show you how to do it if you haven't done that yet.
Where'd you get the 15 from?
I just said we're going to use 15 amp breakers.
Oh, okay.
Yeah, like I said, it could be 15 or 20, and then depends on the area of the house we're talking about. You might have to use one versus the other, and I'm going to point some of those out now as we get into C, the next section, C. But to simplify the questions and to not make them too complicated, I'm just going to give you a determined breaker size. So I'll say, how many 15 amp breakers do I need for 2,500 square feet?
So that's what that 4.16 is, the number of breakers.
Yes, and there we run into not a problem, but a note that we have to remember, which you can write it down, which is always round up, no matter what. Sorry to put it so far from where it's happening, but always, that's the only space I have. Always round up, no matter what. Do not treat this as a math number where if it's, over 5, we round to 5 or more, we round up, or less than 5, we do not. This is a physical piece of material. You cannot buy 4.16 breakers. You have to buy a fifth 15 amp breaker. All right, and you got to remember that for multiple choices, because here is just like the way the questions are going to get structured, and it'll do something like this to you, right? I don't know, but whatever, just to have both of these here. Where you might see 4.1, well, that's closer to 4, treat it like a math problem. It is not. It is a physical breaker, which we have to account for. Because that breaker, that fifth breaker, is dealing with some amperage. There is a little bit of amperage. Now we're going to try to divide these 62.5 as evenly through 5 breakers as you can, but that will be hard. And remember, these are an imaginary 6.25 based off of an estimated calculation, so they don't even exist, really.
Does it say anywhere in the code book, like how many receptacles can be on one circuit?
Great question, and I will answer it. First, the answer is no, but I'm going to give you a rule of thumb that we use in the field.
I was just thinking, you can put like 40 of the receptacles on one circuit, and then the 3 other circuits have like 1 receptacle each, but then would that be code, or like what is the,
Right. Okay, so let's lay out the breakers here. So we'll use this panel as an example. So we have our breakers, 1, 2, 3, 4, and then 5. Okay. So, and this question always comes up. It's been coming up forever. I remember it being asked back when I was an apprentice, which is how many outlets or how many receptacles can we put on one breaker? The code book does not get involved as far as how many outlets you can put. So it doesn't say for a 15 amp breaker, you can only put 6 receptacles.
It doesn't say that.
It does not say that.
So you can put all the batteries on one circuit?
Well, let's think about how we're going to structure this. All right, so let me see how I explain this first. So there's a rule of thumb that we use out in the field to how many breakers that, or how many receptacles that we're going to put on a breaker. But first, let's kind of put that into a situation, because situations are different in all of electrical, meaning I could be dealing with commercial building versus a residential. So let's say in a house, we're in a residential, so we're in a house. We're going to lay out all these receptacles. What you have to do here now, because it does, what it is giving you, it is saying something. It is saying to evenly proportion among the multi-wire branch circuit. In other words, distribute this load amongst the circuits. In other words, of those 62, you don't put 60 on one, right,
yeah,
hypothetically, and 2 on the other. So to your question about 40 on one, and so, but how do we do this with outlets, right? Because I don't know what people are going to plug in where, right? So with the outlets, here's the rule of thumb, which is the rule of 12. 12. All right, and it's 12 points, not 12 anything. It's 12 points. A receptacle drawn like this is worth 2 points, and switches are worth 1. So any combination you want on a breaker, as long as you don't exceed 12. So I can put 5 outlets and 1 switch on a 20 amp breaker. Remember, the switch is going to feed lights. These days, you don't even have to worry about light bulbs in the world of LEDs, but when we say switch, we mean the lights the switches are going to control. But in most cases, again, that's why I say residential, not a hallway in a hospital, talking about a house where one switch in a bedroom controls a light in most cases. Two, couple of lights in the living room, like that. So there's some limit to the light bulbs, or to the lights too. We're not just saying, again, a stadium full of light bulbs. So in this situation, you would run your 12-2 Romex, let's just say. 1, 2, 3, 4, 5, 6 outlets. You're done. Right? There's your one branch circuit with your outlets. If you're going to add a switch to this, then it would have been better to now put your switch, and that switch controls your light or a couple of lights or whatever. Like I said, in a house, you're never worried about how many light bulbs. We're never dealing with 300.
Sounds good. Yeah.
Right? So that's one circuit. And then we do this throughout the rest of the house.
What if you had a surge protector and you plug in a whole bunch of stuff?
By code, we actually do have to have a surge protector in all panels these days. All right, we'll look at it next article. Article 215 says you got to have a surge protector in the panel for residential.
That's
What are those things that you plug into an outlet that gives you like 10 more outlets? I thought that's
Oh, you mean a power strip?
Yeah.
So here is okay. So that's a great point to make. I don't know if somebody is going to connect a power strip, adding 1, 2, 3, 4, 5. So I got one right down there. So I don't know that this is going. This is why I don't want to put 40 receptacles here, because things are going to get plugged in, and what could get plugged in is something that can plug more things into it. Now again, in residential, you are given a 3 watt per square foot. Why the 3 VA per square foot? Why not any other number? Well, because you are giving the house a lot of wattage, believe it or not, per square footage. It's actually the most per square foot of any occupancy. All right, that's in one of these articles. If you would have jumped over and followed some of these, specifically that one, 42. 42 will show you all of the other VAs per square foot for non-dwelling unit occupancies. Hospitals, gyms, auditoriums, you name it, it's got it. So the house has the most because people plug a lot of things into their homes.
Is commercial residential the same as just normal,
In the world of voltage, yes, it's all standard, same voltage, more or less. Commercial sometimes has a higher voltage to deal with, but overall the codes are the same, except in this area of calculating total load calculator, determining the main breaker sizes and determining branch circuit sizes. They do separate them there, but otherwise it's all more or less the same electrical. But residential is just houses where people live, and commercial is places people visit. Now, while the codebook does not say, again, while the codebook does not give us how many receptacles we have to have per one breaker, it does give us a lot of restrictions to how much load can be plugged into a breaker, how much limit do you have there. So here's the problem that could happen if you're an electrician. Let me actually put all this back. If you you're the electrical company, right? If you start to put more outlets here, you just give this person many outlets, many possible places off of one breaker where they can potentially plug something in. So turn on the breakers, person move into the house. If they don't ever use these breakers, there's no problem. Nothing has been. This is why the codebook can't really get into how many outlets you need, because you could potentially be plugging nothing into these outlets. So it doesn't want to tell you how many, but again, it does make a lot of restrictions. So here's what starts to happen. People plug it in, people plug in, people plug in, bring in something to this room. Somebody just bought an air conditioner, wants to put it there. Mini fridge goes into this bedroom. Plug in, and what you're starting to do is add amperage. you're starting to add amperage to this circuit. Well, you are limited to what we said, 15 amp breakers. So at some point, this breaker is going to pop. And now the electrical company has to come back and take a look at the situation and go, okay, you've plugged in a lot of stuff to your outlets, and you're not going to tell the homeowner, unplug all of this. So now what you're going to have to do is you're going to have to go, all right, well, they're going to plug into all of these outlets. They're exceeding 15 amps. Let's say they've plugged into all of these outlets and they're somewhere around 25 amps. So definitely your 15 amp breaker is popping. So now what do you have to do? Well, now what you have to do is you're going to have to divide this circuit. And you're going to have to now run another breaker to the panel for half the circuit. Divide this circuit in half, in other words, so that now you can distribute those 25 amps evenly. Whatever, 15 amps on one, 10 on the other, 12 and a half and 12 and a half, whatever you can. So you already had to do the job of adding, you could have caught this in the beginning. So you're going to have to come back and deal with this as a problem later if you give people too many outlets. Right? If you put outlets, people will plug stuff into the outlets. So as the engineer to the building, if an engineer has been set up to do it, as you, the electrician that's going to do it, because if it's a small house, you don't need to get engineers involved. The electrical company and the qualifying electrician for the company can calculate all this and get the permit for the city. So you are going to deal with any of the problems. So you limit the amount of outlets that you put on a breaker. You set a number. That's why we have that 12 rule, because we've determined 6 outlets on 120 amp or 15 amp breaker in a house. That's good enough. That's not going to lead to problems. All right, all those good questions, because we want to know how many outlets we can put on a breaker. So about 6, and keep that rule of 12 and it'll work out good. Going back here. All right, so this is the calculation. This is the way we got there. So it's been a second since we did it. So let me give you guys the opportunity of coming up with that number on your own. And this is how the question will read next week on exam 1, final and all that, but also just in general, how these questions are going to read. So I'll give you guys a minute or two. A minute shouldn't take too long, but see if you can determine how many breakers. And again, that 15 could be 20. Don't ever settle on a number. It could change in an exam, just to point that out. $1985. That was a good year. I was 10. That was a good year.
I was still in my dad's moles.
Same.
Nice.
I'm a little swimmer.
I believe.
Fastest
Yeah, you guys are the fastest.
I won, Mom.
Every one of you is a winner. Just remember that.
Prize sucks, I'm not gonna
Man.
If you don't ever win another race again, just remember that one you won.
lie. Is it 4?
4? I don't know. I'm gonna slowly start to set us up. We have 4 as the answer. If anybody has a different number.
Scientific calculator?
No, I never. Yeah. I don't.
Yeah.
I don't remember it. I've had this question up for a while, so. So 3VA, don't forget that. If you got this set up so far, you're so good. 5955.
Every year, dude, like what? It's 1,985.
Yes.
I was like, yeah, 1985.
Yeah, that's the square footage, not the year. I don't want to get too far ahead, just make sure everybody's still working things out. I don't want to answer them for anyone. So far you should be here. And I'll point out the 2 numbers that you So you will have to come up with that one, and you will have to remember this one. The question will give you the next one. But you'll have to remember 3VA, and you'll have to remember the 120. So this is 49.6. I'm just going to call that 50. All right, 49.6. We can just round it up. You don't have to worry about the 0.6. That one we do treat as a math problem. So from here it's 15 amp breakers. Yeah, that's looking like 3 and some change.
3.3.
Yeah, 3.3 ad infinitum. So again, very good. Always round up. That's going to always be 4. So answer here would be simply 4. Good. We've done our first load calculation. So 5 breakers in this, or sorry, 4 in this house now. 4 breakers, and again, this is minimum. If somebody wanted to go, you know what, let's just put a 5th one, all good. A 6th, a 7th, an 8th, no problem. This is all fine. From here on out, it's fine. If you wanted to, you're building your house, and you're like, you know what, I'm going to go 5 VA per square foot. I'm going to give myself a little more amperage coverage in this house. All right. Again, these are all minimums in that sense. These are all minimums. All right, so easy to break down. You got 4 breakers are going to go in here, and so nice and easy 4 breakers. Okay, questions, follow-ups. Let me clean this up a little bit. Make it a little neater, because we're going to go from here. Now, the next stuff we're going to look at, this is just going to be highlight, and highlight a couple of things. We're going to move down a couple of articles, not super quickly, but they're not going to require too much in the calculating or talking about too much. But like I said, from here, right, this is our first calculation that we do in the overall, going back to the beginning here, how to determine the number of branch circuits needed for a dwelling unit. So far, all we've determined is the number of general purpose outlets and lights. Again, the overhead lights in the bedrooms and the outlets that are scattered around the house that you can plug in your random stuff to. And those were the unknowns. From here, we're going to get into all the knowns. Everything that we know that has to be in the house. So let's go into section C. All right, there are some requirements now. There are some requirements. So from those general purpose breakers that you put in the panel, you're going to now have to start to add more breakers to the panel, of course. And C sets us up. All right, C starts with small appliances. And it says, small appliance branch circuits. All of these that we're going to read now, 1, 2, 3, and 4, are going to start the same. In addition to the number of branch circuits that you have determined elsewhere, right? That's what it means by required by other parts of this section. You will add to your panel 2. All right, important you highlight that 2 because it's the only one that has 2. Everybody else is just 1. Small appliance is the only one that they require 2 breakers in the panel. 2 breakers in the panel for small appliances. 1, 2, small appliance. All right, the first 4 here, I'm going to label. I want to label all of them. And this I'm just going to put as general lights. All right, general lighting. Now, these 2 small appliances, while the general lighting could be 15 or 20 amp, these here have to be 20 amp. What they mean by small appliance is another unknown. All right. Small appliance is another unknown. That's why it's the next one, because it's the other one that we don't really know. Same thing with the laundry circuit. We'll get to it. But a small appliance is an unknown. What is a small appliance? Well, a small appliance is a blender, an air fryer, a coffee maker, a microwave. Any of these small appliances that you can move around the counter, or put it in a drawer or in the cabinet. Take it out, only use it, but it gets moved around the counter space.
What about a waffle iron?
A waffle iron, yep, George Foreman grill.
What about a panini press?
Panini press as well.
What about a hot dog roller?
Also would be considered a small appliance.
Well, you're gonna need 20 circuits in your house. Yeah.
Yeah.
He's building
That's a good point.
a station.
Hey, should I borrow 76?
That's a good point. If the person has a large enough kitchen, well, then you have to consider that they might have more stuff. So always the size of space, right? Square footage, VA, and all that is going to be something to consider. So if you have 2 breakers, right? And here it's going to be a little deeper than we need to get into this right now. But if I have a 20 amp breaker, and these outlets are going to go into the kitchen for small appliances. First of all, they have to be GFCI, as we learned yesterday. 1 outlet in the kitchen, 2 outlets in the kitchen. 3, here's the thing about small appliances. They're not low amperage things. Blenders draw good amps. 6 amps, 8 amps even. Same thing air fryers. When they're on, they're on. So while small appliances individually are low, individually they're 6, maybe 8 amps, that doesn't seem like a lot, but if your microwave's on and you got the coffee maker going on in the morning and you got that panini press kicking, that's going to accumulate maybe more than 20 or pretty close. So my point is, you don't want to put too many outlets, same thing, on one small appliance breaker. That's why they make sure that it's 20, bigger than, you got to be bigger than the 15. They want the maximum they can put. 20 is the max. So you also want to limit that. So again, engineering, we don't have to go that far deep into it. This is more of an engineering thing. We just have to know the breaker we're putting there and or replacing. If you have to remodel a kitchen, you got to know what breakers you're bringing into that kitchen area. But that's what it's for, small appliance. So while again, 2 is minimum, as you were just saying, if you own a hot dog maker and a panini press and you got a bunch, you can put 1, 2, a total of 5 small appliance loads if you want into a large enough kitchen that would require it. So all of these are extras now. So I would have to charge you for that panini press hookup. Big money. I'm not cheap. All right. So there's the first one. All right. There's something here we'll get to later, 52B, but not worried about it right now.
If you
Go ahead. Go for it.
If your main panel is stacked out already, and you have
Okay.
you have 125 amp main and you're using already 110 amps or something, and you want to add a car charger, you have to not only upgrade the main panel but have them pipe out 200 amps from the utility.
Yes.
Yeah.
I just ran into that for a client, not client, just these people I knew that they got a Tesla, needed a Tesla car charger. I got to the house, 150 amp main breaker was the voltage that I had to deal with. In fact, and I'll show you this because it is important that we know how to deal with this. This is a good question that leads me into. Here we go. Let me pull up. This is the panel. This is literally residential. You were saying it's gross. There it is. Here's our residential panel. Yeah. And this is a fairly new house. It looks bad, but it's not terrible. But it looks bad, but it's not terrible. I'll come back to this. I'll talk about this guy later. All right, these are all our neutrals and grounds. So if you can see, yes, this is full. This panel is full. There are a lot of, look at all my single pole breakers. All of those little single poles are for branch circuits. And probably, this is a 2-story house, very big house. Probably most of them are for either the general lighting loads, small appliances. There's going to be a laundry circuit in here, a couple of circuits, one for the garage and things like that. All the ones that we're talking about right now. So they are full. In fact, not only are they full, on some spots, like counting on the left-hand side of this, starting with the first double breaker, second double breaker. After that, if you count 1, 2, 3, that breaker has 2 wires on it. And if you look at the bottom right of this panel, you have the same thing going on. So just to point out, not only was this full, they already were doubling up. So here's what they asked me. Well, go ahead.
That's legal though, right? You can double.
Oh yeah, but look, this is what happened. That house had a load calculation done like we're doing now,
Yeah.
and they did it in, the 70s. I think that's when that house was built. And then more things arrived to houses.
Yeah.
People bought more stuff, so more things got and then they're full. Another thing too that happens is, let's say you call me over to, hey, I want to add an outlet over here. Okay, I should just pick up an already existing circuit from any outlet that you have in the house and just pick it up from there.
Unless it's going to be a small appliance, right?
Unless it's going to be something, yes, exactly. You told me I'm buying a compressor. Okay, I'm going to give that compressor its own. I'm buying a freezer for my garage, big amperage freezer. Okay, yes, something like that, yes. But you just want to add a circuit, and it's not that big of a deal to add this circuit. I should just tie it into another breaker. But what people do is they don't want to do all that. They just add another breaker to the panel and then run mine outlet. And then sometimes in the future, same thing. They were going to add some new thing that could have already been thrown on another breaker. Instead, they just add another breaker. And so eventually we're full. So this person asked me to add the car charger to this. So how do you deal with that? First of all, how do I even add another breaker here? And this breaker is a 150 amp main breaker. All right, now I'm not going to get too far into this, but just to set us up. The things that I had to do was measure the amperage that the house was consuming at that moment, or in a few instances, like in time, you want to measure at a couple of times during the day as to how the amperage is going. And then knowing how to move those breakers around using those tandem breakers, the ones that you can stack 2 circuits on one breaker. They come with 2 little handles on one small breaker. I had to add a bunch of those. But my point was, all right, the point to that is also that when these things are calculated, all of these minimums that we're giving this is why it's a good idea to also go a little bit above the minimums too. Add an extra general lighting, add a couple things, just so that your main breaker could be large enough to handle future things. Now, did we predict in the 70s that EVs were gonna, no way, even in the early 2000s, 2010, this wasn't a thought. So there was always going to be things that eventually max out the panel. Now, to your question, yes, if you have a panel maxed out, nothing else can be done, we've exceeded all the options we have, then yes, you have got to increase the main on that, and it will also require the utility company to bring you a larger conductor size down too. So we need permits for all that. And
so what you think will be like a $600 job is going to turn into like a $16,000.
Yeah, that around service change like that with the wires, I'll do it for about $3,000 to $4,000.
But for like, if you have to dig out to the utility.
Oh, no, we don't. Well, that's for residential. Usually, it's just the pole bringing the wires down.
Right.
So we don't do that far. We just set up our. Do this in a better color. We just set up the weatherhead. We just set up the new panel with the 200 amp now main breaker. We set up the wires, and then the utility company brings their wires, and they are the ones that splice.
Like all of Irvine is underground, and then.
Oh, I see. Okay, so yeah, you would have to do the dig, and but then again, you just run the wires over to the utility company, and they pick them up from there.
Can't you just jam some pennies in it?
No, again, you could, because what did I know about that panel? What I knew about that panel is every one of those breakers is barely being used. I measured the amperage on every one of those 20 amp breakers. Most of them have 0 on there. Some of them had 2 amps. When I measured the amperage on the main, it was 25 amps. That's how much amperage was in use in the house. So I knew that people just kept adding breakers to this for minimal usage requirements. Another thing about small appliances to consider: how long are they on? Not too long. They're not continuous loads. They're a minute or two. How long are you blending for, right? How long is that panini taking?
Hot dog rollers and all day.
How long is the hot dog? Well, that could be an all-day affair if you're running a 7-Eleven at the house. But I'm just saying, these are momentary loads. So this is all, this leads, as it is right now, it leads to bigger questions that, you know, a lot of times you try to catch as much as you can. You know, try to put, maybe let's add another small appliance load here. But new construction these days has to account for a lot of stuff. There's mandatory EV stations are now going into houses. So these days, it's like one's going up, one's going down. Lights went down wattage-wise really low. So we gained a lot as homeowners as far as wattage consumption when we switched to all LEDs. All of the components that you're buying these days are very efficient. All of our air conditioners, refrigerators, and all this, very efficient. This is why it's important, while it is a big expense, to update your electronics every 5 years, I would say, because you're just wasting more electricity now. So while we are now including an EV car charger, again, keep in mind, person might not have an electric vehicle, the code is now requiring them in houses. You know, building codes in areas are requiring them as well. So we are adding amperage to panels, and panels are, they're, you know, most average homes now are getting about 200 amps. Whereas it used to be about 100, or like that 2-story house that I showed you was just a 150. These days, that would be 200, 300 amps.
If you didn't upgrade and you just added it and it went over average, would you start melting like the main breaker? And
So you wouldn't, you would just trip the main breaker.
okay.
Yeah, and main breakers, tripping 150 amps is not fun. You're putting a lot of stress on that panel. That's a lot of amperage to be playing around with, having a breaker trip and then resetting it and having it trip again, because that's what's going to occur. They're going to turn it. So we never want to overload past the breaker's ratings for those reasons. Especially, you know, you trip a 20 amp breaker, not a big deal. You start tripping a 150, you're standing in front of it, turning it on, or the homeowner is. This can get dangerous. There's where melting can happen, and yeah, sparking, and I'm not saying explosions are that dangerous, but it is just a bad situation to trip a main breaker.
Your panels and stuff, they'll have a higher tendency to melt probably, right, and not trip.
The older ones?
Yeah.
Yeah, absolutely.
Hopefully not. Sure.
So, and this is getting back to the section that we're going over now, and all of the things that we're going to be looking at now. This is why we have these mandatory numbers. Small appliance circuit, again, let's just highlight this real quick. 2 at 20 amps. A laundry circuit, in addition to the number of brand circuits required elsewhere. This one is 1 additional 20 amp brand circuit shall be provided. So in the panel, there will be a 20 amp breaker provided for a laundry circuit. Now, the house doesn't have a laundry room. Okay, we're thinking new construction. Almost every house now in new construction world gets a laundry room. A laundry room. They might not give you the appliances, but you get the room. You get the outlet, you get the hookup for the dryer, you get the water hookup. This is when you're building a new house, this is what you're doing these days for it. All right, that's probably been a thing for 20 years. You at the very least bring in a room, a closet. You will have the water and the vent for the dryer vent and the hookups in there. Person doesn't have to buy one. You're not forced now to buy a dryer or a washing machine, but it's available. All right, so in the house there will be again a closet, a room, a something where there'll be an outlet there, or two outlets there with a breaker in the panel representing that outlet. Trying to draw it a little bit straighter because I'm going to add another one. That circuit will be the laundry circuit. Now, the laundry circuit is another situation in which if you put an outlet in this room, right, you have this room, you put an outlet in here, and then you're going to put the dryer outlet. I'm just going to put a D on. This is where the dryer is going to go. Dryer is a completely different unit, very large 30 amp unit, special outlet, gets its own direct breaker. So this is going to be a individual appliance, which we'll deal with later. I'm talking about the regular little outlet that's in there. Well, if you have an outlet in there, what is the person going to plug into that? The washing machine. If it's a little room and that's all you can fit in there, a washer and a dryer, you don't have to worry about another outlet in there. But if it's a larger laundry room and now potentially the person could bring in something else here, you might want to put another outlet in this room. And that one, so 2 outlets for this room. All right, now, you know, is it going to be tied into the other outlet here in the living room other side of this? No, this is dedicated now. All right. So again, depends on the washing station you have or laundry room you have. It could be small, it could be a little bigger, requiring another outlet. Even another one here. It doesn't matter now at that point. You can put 1, 2, 3 outlets in here. All right, you're going to have a light up here as well. Coming from, I guess I put the switch over here on this side to the light. All of this would be tied into the laundry circuit. All right, the light in that room and 1 or 2 or 3 outlets, however many they put in that laundry room. Now, can you have a second laundry circuit? Because, you know, person wants to put another washing machine in there. Sure, you can put a second laundry circuit in there. Got to have a minimum of 1. All right, the next one is bathrooms. Same thing. House will have a bathroom, sometimes 2. 1 breaker in the panel, 20 amps. And this one just went up. I don't know if exactly a little recently, but it used to be 15 was allowed for bathrooms. Now it's 20. And you have to have 1 circuit. Remember, this doesn't mean 1 outlet. All right, I want to make that important note. This is 1 breaker in the panel representing the bathroom. All right, this is the bathroom's representative. There could be 1 outlet in that bathroom. You can have a nice big giant bathroom with 10 outlets in there. Again, don't put that many on a breaker, but I'm just making a point. It's the breaker we're talking about now, not the amount of outlets we're putting out there.
I said we put 12 outlets on a breaker.
Yeah, do it. You'll get a call from the homeowner at some point. Hey, this breaker won't stop tripping. Now, what if there's 2 bathrooms? Then each one gets its own breaker. Okay, next one, don't worry about that exception for the bathroom. The next one is the garage. Again, you don't have a garage, well, of course, then this does not apply to that house. If we're talking about an apartment, then no, this does not apply to the apartment. All right, so if the house has a garage, then that garage will have a circuit dedicated to the outlets inside that garage, right? In addition to 1 20 amp breaker, branch circuit, shall be installed to supply receptacle outlets. All right, including those that are required, and we'll get to the ones that are required. All right, which is electric vehicle stuff. Sorry, it has to do with whether or not the garage has power. Right? Some garages don't have power, and you just open the doors manually. All right, if you have a garage with no power, then of course no circuits are required. All right, so again, another breaker here now represents if you have one, a garage. All right, there's our garage. Now we're going to pause here at this group, not pause the day, but pause as far as talking about the things that are going to go into this panel. All right, because actually that's as far as 210 covers. 210 covers up to that garage. It doesn't get into anything else from here. It's covered things that are going in the kitchen, laundry room, bathrooms, general purpose receptacles, and if the house were to have a garage, then the outlets in the garage as well. All right, now, things that haven't been covered are the dryer, EV systems, again, electric charging vehicle stations, the oven or range as it's called, air conditioning system isn't covered. All of that we will pick up in Article 220. All right, this is just, again, as I said, this is just the beginning of a much larger calculation. All right, so what do we know how to do now, or at least have some information on how to do? Determine how many breakers I need for my general purpose outlets in the house, and how many breakers I need for a laundry circuit, bathrooms in the house, small appliance loads, and a garage. We've done some filling of our panel. All right, we'll get back to these calculations in Article 220. So far, so good. If anybody has any follow-up questions to the calculations, if you got this 3VA, if this made sense, then we are good to go. I will post another video today with a little bit of this. I'll probably ask a couple of questions. All right, so we have the next one, AFCI. We'll continue on our journey through Article 210. Our next article is 210.12, AFCIs. And here the same thing with the GFCIs. There's nothing special about this article other than B, right to the right where it says dwelling units. And that is the location of where you have to use AFCIs. And here's the thing about AFCIs. Everywhere. Where do you use AFCIs? Everywhere where GFCIs aren't required. Right? Everywhere where GFCIs aren't required. And you'll notice kitchens, which GFCIs are required in kitchens. AFCIs are also required in kitchens. This gets into a little tricky situation about appliances and the walls in the kitchen versus the countertops in the kitchens. We don't have to get too far down that discussion, but if it's a countertop receptacle in a kitchen, if it's close to a sink, then GFCI. If it happens to be, we're in the kitchen, but we're nowhere near the countertop, we're just over by the door in the kitchen, there's an outlet down there, you know, in the regular outlet level, not countertop. That one, far away from the sink, AFCI. So we don't have to get down the two, you know, far down, when are we going to use GFCIs? But just in general, kitchens, normally you're going to fall under GFCIs for kitchen, but it does show up, as you can see here, under AFCIs as well. And it's the only one that overlaps. They don't have bathrooms here, for example. All right, you can see the list, all 14, no bathrooms. No garage. Right, look at the list here. Let me see if I can put both on screen here. There we go. No garage. No outside. Outside outlet, those have to be GFCI. The garage, GFCI. If you have, we are required to have outlets outside of the house, GFCI. Bathrooms, GFCI. So as I said, GFCI was more water safety. All right, the only thing I do want to explain is what is an arc fault versus a ground fault. You may know this, you may not know this, but I do want to explain this because it's important that we know the differences between these two. One is safety, one is preventative. I wouldn't say safety so much as preventative. All right, GFCIs, and I want to bring those back here for a second. Oh, last thing to mention about the article is just make a note of that. Just have highlighted here dwelling units and areas that I have to have AFCIs on. That's the kind of questions you're going to get about AFCIs. Which of the following locations require AFCIs versus GFCIs? So GFCIs protect from two things only. They're sort of the same, but not. But they're sort of the same. Ground fault, it's in the name. And short circuit. Now, a lot of people think these are both the same. They are not. All right, so a GFCI protects from a ground fault and a short circuit. All right, these are the two situations that could put equipment in danger, but more so people in danger. Right, that's the real concern with GFCIs. Now, let me just explain the two, because if anybody asks you what a short circuit is, and you're in an electrical school, and you say, I don't know, that's not a good answer. So here's my hot, here's my neutral. What is a circuit? A circuit is the complete, right? That's a circuit. This is a load, right? So we have a load, and this is how we have a completed circuit. All right, we can have a switch and all that, doesn't matter. So this is a circuit from the hot to a load. The load has a very important feature, resistance, and then back to our neutral conductor. A short circuit is you've shortened the route between the hot and the neutral. Now, are the hot and the neutral together? Yes, they're together at the load. Right? They're not touching. You're not touching the hot and the neutral together. The light bulb is using the hot and the neutral. It has resistance and etc. We don't have to get into all how a light bulb works, but it's using the hot and the neutral together to create light. How do you shorten that? You shorten that by just simply bringing those two together. So when the hot and neutral, and I'll just put it like this, you can expand it as a explanation if you want. A short circuit is when the hot and neutral come into contact. It's the shortening of the circuit. Now, what really happens in a short circuit? Well, resistance goes away. You lose R. That's the feature that happened in the short circuit. So technically, again, the short circuit can happen here at the load, the hot and the neutral touch. It can happen down here at the junction box. Somebody could have cut our Romex, leaving the panel, who knows where the short circuit happens. But that's what a short circuit is, when the hot and the neutral come into contact with each other. All right, massive amount of amperage goes into this circuit, but we don't have to get into the calculations. A ground fault is different. A ground fault is when the hot and the ground come into contact. The hot and the ground are never working together. The hot and the neutral are working together. They're working together to create light on the light bulb. The hot and the ground are not. They never work together to do anything. The hot is doing his thing with the neutral. The ground's over here just making sure all the metal pieces are not energized. So the ground, yes, the ground is here. And it's going over to our load as well, right? Connecting to the metal of the light. But when do the hot and the ground come into contact? Not. So usually a ground fault happens when, odd things like residential Romex is why I don't like Romex too much. Bare copper wire there. You start to stuff your outlets into the box. Your hot's touching, or that bare copper from the Romex is touching the outlet. You turn the breaker on, you get a ground fault. All right, again, both are the same. But the idea of the GFCI is to protect against it. So what does it mean to protect against a short circuit or a ground fault? Well, let's say that this is a GFCI here. All right, we can ignore now So here's our GFCI. So somebody plugs in something into this GFCI outlet, and now they're using whatever, a hairdryer in the bathroom. So here's the thing about a short circuit. Short circuit is going to trip our breaker. Right? If you don't have a GFCI, right, say we didn't have a GFCI here right now, and we have a short circuit when the person is holding this. Here's our person, Exhibit A, holding the load. If there's a short circuit here that could potentially hurt them, or short circuit right where they're holding it, that would be the worst one, where the short happened here, where the person's at. For this short circuit to cause the breaker to trip, it has to make the journey through the conductors all the way back to the panel. Technically, it takes a different route. It goes to the neutral to the ground to the transformer, all the way back. It takes a gigantic route to get there. But in other words, it has to make the journey back to the panel to trip the panel. So this takes time.
It's just like a split second. Like, how much time is it?
Exactly. This takes time. It takes somewhere around, believe it or not, 1 to 2 seconds to trip when you have a short circuit. If you were to grab the hot and the neutral and touch them both together, you'll hear a zzz, and in about a second, pop, that breaker will trip. Now, here's the thing. The distance from the short circuit to the short circuit protection device, let's call it that way now, the distance from the short and the short circuit protection device are going to equal time. All right? These are conductors that our short circuit is flying through. Conductors have resistance. There is just a limit to how fast the short circuit can get back to the panel. So
GFCI plug will trip instantly because it's right there.
Exactly. Now you got the idea. The GFCI is right in front of the person. So that's what the GFCI did. It cut a second or two. Doesn't seem like a lot, but when you're getting shorted out, a second or two could be a problem. So therein lies the job of the GFCI. This is why, again, think of water when you think of GFCI. Wet locations. Outside, kitchens, near sinks, bathrooms, all that stuff. Because we want potential pieces of equipment that we know are near water and near conductive materials like that. If they get shorted out, could potentially be a real hazard. So those should be a GFCI. The arc fault, well, it should be in the name, right? This protects against arcs. So, what is an arc?
Well, yeah, if you touch the ground and hot together, you're still gonna get an arc, right?
If you touch the ground and hot together, you're still gonna get. Say that again.
You're gonna get an arc if you touch the ground and hot together, right?
Well, yes, you're gonna get an arc there because you are. Yeah, when you ground out.
How's that not a ground fault though? It's like both.
Well, okay, so let's talk about. That's why I said what is an arc. So, and what do they mean by this arc fault? Well, what you are describing by a hot and a ground touching is something that welders do. That is called welding. There is a welder called an arc welder. Because an arc welder is somebody holding the hot conductor. The piece of metal that you're going to weld is grounded to your welder. Your welder grounds to that, and you are DC current, so we're okay. You are grounding. That's what welding is. It's literally. Now, there is an arc that happens while I'm doing that, and it's just the sparking. So an arc is just the sparks made by current. Right? That's what an arc is. It's the sparks made by current. So yes, when you ground fault, when you short circuit, when you touch the hot to the back of a panel to a junction box, that's all grounding. When you weld, you're going to see sparks. But that's not what the arc fault protection device is doing, or an AFCI receptacle. This AFCI receptacle is not about sparks and welders, what this arc fault receptacle is doing is protecting against an arcing that happens when people unplug devices or loads. And here's the thing that has to actually be going on, which is this load in the on position, right? You got the lamp on, you got your computer on, you got whatever it is on, and they just unplug it because current. All right, what is arcing? Arcing is the sparks caused by current. So when this is on, whatever it is, whatever load it is on, and it's generating some amperage, whatever amperage it is, the more arcing. All right, if this is 2 amps versus 20 amps. So let's say you have 5 amps, you got whatever, a couple of lights plugged in, or you got a light plugged in, drawing 5 amps. If you don't turn this light off and you just unplug, as you're unplugging, you are disconnecting 2 points that have current running through them. So as you try to pull those two apart, the current is like, hey, I was just over there. That was my route. I love that route. I want to, and eventually there isn't enough voltage pushing this current that it stops. The further apart you get, the arcing goes away. Now, higher voltage, you got 1,000,000 volts, then you gotta really pull apart for 1,000,000, because that's a lot of voltage. It is going to arc over. So when people are unplugging, that's what it's for. That's what the arc fault protection outlets are for, or devices which become outlets. So these days, and if you ever seen them, it's a little door, it's a little flap on the neutral and the hot. As soon as you pull the plug out, they close. Any arcing that happens stays inside. What they don't want is arcing on the outside. And again, remember, the code book is regulated by the fire department. So I'm guessing the fire department has determined that people unplugging from outlets, the arcing that happens there has caused enough fires that they're like, hey, we need some special outlets now. So everywhere in the house that doesn't have a GFCI these days must be an AFCI receptacle. And remember that. If you ever go to anyone's house now and an outlet has broken in their house, it could be a 70-year-old house, and you pull that one out and you put a new one in, that new one has to be AFCI on. Don't forget that when you go to Home Depot to buy these outlets. The new ones now have to be AFCI.
So we just never use normal ones ever?
Never again. Even though you can buy them and you can buy them and you can buy them, and I buy them and I install them. Yeah, you have to have AFCI. Residential. The reason why they sell the other ones is because commercial buildings don't require that. So,
That's the cheaper one.
yeah, and it's cheaper. Yeah, you go to the box, they're 89 cents. I'm not going to go buy that $5 one.
When you're replacing a panel for a main panel that doesn't have AFCI breakers, you don't have to put AFCI breakers on?
No, if I don't know how the AFCI rule for breakers is, but you can still, there is grandfathered in things. So if you're replacing an old breaker, I don't think you have to upgrade it to an AFCI breaker, but I don't know that one 100%.
For the whole main panel?
Oh no, if you're doing a complete service change out, everything has to be brought to now code. So yes, if you're doing a whole panel change out, then everything has to meet today's 2023 code. If the code says every breaker has to be AFCI, now the code doesn't say every breaker has to be AFCI. This is kind of a little bit what this section goes into, although I don't like to dive too deep into it, but it is going into a couple of things here where you could just have either or. Either you have the outlets or you have the breaker. In some cases you have to have both. So it gets into a bunch of different scenarios. But yes, and then keep that in mind again. That's why I said, your friend calls you over and says, hey, my outlet burnt out. You're like, easy fix. Put a new outlet in. That new one has to be AFCI now. They're like in their bedroom or something. So they sell the old ones because you have plenty of places that are in houses. You know, if a church has a burnt out outlet, they don't have to have AFCIs. If a school, if we go to change an outlet for one of our outlets at the school, they're regular 120, 20 amp outlet, just buy a regular outlet. It does not have to be AFCI.
I'm just gonna bulletproof one.
There you go.
All right, we'll wrap up there. Tomorrow we're going to get into the last bit of calculating that we'll look at, which is calculating wire sizes, breaker sizes, and dealing with voltage drop. After that, that'll wrap up our 210, and that'll wrap up our week. So let me pause the recording.